Okay. So we're going to stick with the same thing we were doing last week, right? Which is we've got an outcome variable. We have a couple of different predictors. And last week we saw, that we can have more than one X because if you're coding a categorical variable with three or more categories, um, you have to have at a minimum two dummy predictors that code for that. This week now we're going to generalize it completely. We're going to allow these X's to be anything we want. They can be numeric or continuous like age. They can be ordinal categorical, so like rating on a scale of 1 to 5. They can be a factor, whatever. Doesn't matter what scale of measurement, what distribution the X's are, there's no issue. The only thing we kind of worry about a little bit, although it's not a huge deal, is for these categorical variables, and really any variable that we use as an X, we do want to make sure we don't have a restricted range. Or for a factor, we want to make sure that, let's say we got 200 people and we're interested in, any gender effect. We'd like to have it not be the case that we've got like 190 females and 10 males. We'd like the categories to be a little bit more balanced, but even then, it's not a huge issue. So point being is that some people get confused as to whether the X variables need to be normally distributed, and that is just not true. Y doesn't even have to be normally distributed, although it's helpful. But indeed, it's still okay. This week, we're going to start to really want to think of the model in terms of its expected value, right? Because that's actually what we're predicting. And I'm going to spend some time on this conceptually, that really what our regression model does is it gives us the expected value of Y for any particular set of X value. So our data points are going to consist of, somebody having an outcome and then, 3, 4, 5 different predictors. And so what the model gives us is what should be the mean, Y value. What's the average Y value for someone with those characteristics? That's what we get out of a regression model. And so the betas are always interpreted that way in terms of what's the expected value of Y for some value of X. Now, remember the goal of regression, because that's like, okay, that's fine. But like, why do we do this scientifically? So follow me here. Ordinary regression utilizes a least squares criterion, which in statistical decision theory is what we call a loss function. It's basically a way to capture, how good we're doing with our model. So what we try to do is we try to minimize the prediction errors using their squares because they can be negative or positive. Remember also that a prediction is just the value of Y that we produce from the model. And so for every person, we have their real actual outcome Y and then the model prediction. And what we try to do is get those to be as close as humanly possible, given the data that we have. So here's then where using multiple predictors is helpful, both from if your goal is predictive accuracy and if your goal is, scientific inference about is this variable important, right? The magnitude of the betas, which we'll also call regression coefficients, the magnitude of those numbers relative to their variance helps us understand if that predictor accounts for a good deal of variance in the outcome. That's what the t-test and f-tests of predictors are about. They're going to be significant if beta is big relative to its standard error. It means that it matters, it helps us, right? So if a predictor like age accounts for a lot of variance, it's going to reduce the residuals, making the model fit better. And logically then, if it makes the model fit better, makes prediction better, then it must be important, scientifically, perhaps. But that part does require scientific logic, right? And so that's, again, part of your analysis assignment is not to just, pick an outcome and fit a model. It's pick an outcome, look at what previous people have found about it, perhaps a theory about why it should be affected by certain things. And that's sort of, in science, the route that we take, is we try to choose predictors both for their substantive value, so scientific value. Does age matter when predicting, cholesterol? And also then, and usually age is in the model not as the main variable of interest, but also we choose predictors to try to adjust our models, make sure that given someone's age, that another important predictor matters. And that's what we're going to discuss today a lot, to try to get an understanding of when we have multiple variables in a model, why is that good, and then what does it mean? And now we're going to kind of dip into when we have multiple regression coefficients. What do they mean? Well, they're still just as they have been, right? The betas, the weights, they're an estimate of the linear association between x and y, as they have been. But now that we have other variables in the model, really what they are is their relationship between x and the residual variance in y after all the other predictors have been dealt with, right? So another way to think about that is that in a multiple regression model with multiple independent variables, the beta coefficients, the regression weights, are giving us what is the unique contribution of that predictor in the model, controlling for all the others. And so there is a concept in correlational analysis that's analogous, and it's called the partial correlation, right? And so each beta has, as in with simple regression, in week 6, we had one variable, we can get a regression model, and then we can also look at its correlation with y as two essentially pieces of information about the same thing, the linear relationship between x and y. Now, when we start to add more variables, what we're doing is we're adjusting our estimate of the linear relationship for the presence of other pieces of information. Like, so for example, if I know somebody's age, so age is going to relate to a lot of things, right? Age relates to cholesterol. So let's say I'm interested in the effect of some treatment on cholesterol, and I include age in my model, along with some indicator variable about treatment. What I'm doing there is I'm asking a question, okay, I know that age relates to somebody's cholesterol. So given someone's age, so like just let's say among 40-year-olds, does treatment still matter? Among 30-year-olds, does treatment still matter, right? So when we add more predictors to a multiple regression model, what we're doing is we're trying to adjust for the presence of those variables, which can be very, very helpful in observational research where we don't have control, we aren't able to randomize group assignment, right? We're able to, because what randomization does is it tries to get a good mix of all of these background variables like age, sex, race, socioeconomic status, underlying health, whatever. We try to get those things equal in both groups so that they don't confound or mask any treatment effects. We can do that statistically too using multiple regression. So let's pick an example, not the cholesterol one. Let's pick a simple one where we have two numeric predictors and a numeric outcome. So in general, so we started with points last week we had points in a more than a three-dimensional space, but it wasn't really this type of issue, right? We started in week 6 with just the scatter plot, right? Two-dimensional problem, an X value and a Y value. In general, we can have as many dimensions as we want. So let's look at a three-dimensional problem. We'll take our first predictor to be age, our second predictor to be a person's date trait anxiety measure, and then our outcome to be health-related quality of life. Our data now are three-dimensional. We've got people will have an X value, right, a point on this axis, an X2 value, and a Y value, right? So there would be a triple. It's in three-dimensional space. And then our regression equation is actually a plane. We fit a surface in that space. And so I ask you then, what do the betas represent? Well, it's not really clear, right? I mean, so we know that in a two-dimensional problem, a beta represents the slope of the best fit line to those points, right? So what I'll show you is what the betas represent in higher dimensional problems is they're still slopes, right? But what we have to do is we have to kind of take a slice of our data, right? So we fix the values, say, of X2, and we project our problem just onto the two-dimensional YX1 surface. So we get a slope, but it's not, but it's a slope that's affected by the other variables in the model. So we're going to generalize what we already know, right? The intercept is still a value. It's the expected value of Y. It's a mean for anyone who has all of the X's equal to 0, which usually makes no sense. In most regression models, the intercept is not going to be an interpretable value. Last week it was when we only have a dummy variable or two. So we only have categorical predictors. The intercept is the mean for one of those groups. But now when we have numeric, a mix of numeric and categorical and whatever, the intercept is going to be the value of our outcome, the mean for, people of age 0, in some group who also have anxiety equal to 0. So, age equal to 0 makes no sense. So generally, we're not interested in the magnitude of the intercept, but it's there. The regression coefficients still represent a slope, right? Slope is a change in Y when X changes. So slopes in linear regression, the number is how much we would expect Y to change when X changes by 1 unit. But now we add this qualifying phrase that expected change is with all the other X's held at a constant value, right? Which is also to say that we're conditioning on the other values of X or we're controlling for them. What that means mathematically is in multiple regression, the betas give you the change in Y for each unit change in X that's unique to that relationship. So basically, if some of our variables are almost always correlated. Like if we have height and weight in the same model, they're going to be correlated. So a multiple regression model allows you to look at these unique contributions of additional predictors that might be correlated. It allows you to sort out correlational relationships in a better way. And then it also allows you to adjust beta estimates for the presence of other characteristics. So let's think about our problem again, right? So in this situation where we're trying to predict quality of life, our intercept would be the expected value of health-related quality of life for people who have no age and no anxiety, which again makes no sense. But it's important that it's in the model. It provides a basis for the rest of the model, right? Sometimes, and we'll do this in PHS 615 for those of you who will take that class, sometimes we do what's called centering our X variables, in which case we can make the intercept make sense, but we're not going to do that in this class. The beta for age, right? So beta 1, if X1 is age, what does that mean? It's the expected change in health-related quality of life when age changes by 1 unit for any value of anxiety that we like. So take just the people who have no anxiety, right? Beta 1 applies to them. Beta 1 should also, and this is the difference between this week and next week, is for a simple model like this, we assume that the betas, this beta for age holds for anyone of any value of anxiety. We'll see next week what happens when that isn't the case. That say, for people with low anxiety, age relates to health-related quality of life, but for people with high anxiety, it doesn't. That's certainly something that can happen. And in order to test for that, we have to fit a model with interactions, which we'll learn about next week. So this is just to say, right, what each regression unit or coefficient represents is, so we'll look at beta 2, X2, right? This is now the relationship between anxiety and health-related quality of life holding age constant, right? So again, pick the people that are only age 40 in our study, right? Beta 2 describes what happens to quality of life when in those people, anxiety goes up by 1 unit. But for any, what we call additive regression model, like the ones we're going to do this week, this beta applies again to any of the strata for age. So we'll see a more concrete example of this with a grouping variable in a little bit. But this is the thing I want you to kind of, nothing we do this week will be really that much different in SPSS. We're just gonna have more stuff. The trick is understanding like what we get when we add more variables. And again, it's where we get a more pure look at the relationship between an X and a Y when it's correlated with another predictor. This is what's called collinearity, and this happens all the time, right? Especially in observational data. And indeed, one might argue that this is the purpose of multiple regression, is you would expect that your predictors might be somewhat correlated. So that if you were just doing what we call zero order correlations, which are just regular correlations, if you have correlated, if you have two variables, two predictors that are correlated with each other, then a correlational analysis looking at the relationship between the predictors and the outcome is going to be misleading. One caution, however, so it is pretty much always the case that your predictors are going to have some level of correlation. One thing to watch out for, though, is when you're doing multiple regression with a lot of variables, if two or more predictors are too highly correlated, that can mess up the model. That's well, collinearity is what that really refers to. Some people call it multi-collinearity. It's basically an issue with the mathematics. It throws a wrench in what SPSS is able to do. So here's the correlation matrix for these three variables. So again, health-related quality of life is the outcome. Here we see its correlation with anxiety. This makes sense, right? A negative, almost 0.6 correlation. So people with higher health-related quality of life tend to have lower anxiety, vice versa. Here's the correlation between age and anxiety. It's actually not too highly correlated, which means that when we're looking at this correlation between health-related quality of life and anxiety, we put age in the model maybe sort of just as a background variable, but with or without age in the model, we're going to see this negative relationship either way. But it's helpful to fit a model with age. And again, when we're doing observational research like we do here, right, we can't fix someone's level of anxiety. We often include age, race, sex in the model just to basically provide a little bit more precision when estimating our beta, right? So here's our estimated regression equation. Again, we have an intercept.
Just a question for you.
Yeah, go ahead, Mike.
Would we ever use this as a reason not to include a variable?
Use what? Clarify.
Well, the low beta.
So yes, we're going to discuss this next week a little bit, although it's a very big problem. I'll talk about it a little bit later in the lecture too. It's the problem of variable selection. And people, there's different schools of thought on the use of so-called non-significant covariates in a model. Some people, myself included, would argue it's important to include it because it aids in precision. Whereas others, let's say you've got a data set with like 50 potential predictors and you don't really have a strong feeling about any of them, or you're interested in maybe including all of them or as many as you can. There are procedures where you would only include a variable that reaches some level of significance in initial model testing. So it's really, it's a function of your goal. If your goal is precision of estimating the other betas and also in making the predictions, and you have a pretty big data set, then you include any substantive predictor or thing you think is important to control for, even if it doesn't have a large beta where it's not significant. If you're not so much interested in, I guess, a model that reflects reality and you're just only interested in predictive accuracy, and you can arrive at that with some model with just only significant coefficients in it, then that's fine too. I'm kind of split. I mean, it kind of depends. So some people, to answer your question more straightforwardly, some people might toss age out of the model. They say we don't need it. And some people might say, well, it's kind of an important control, so we leave it in there.
Thanks.
Yeah, no problem. So as before, we're going to still, even if something's, not significant, we'll still interpret it, right? So let's take a look at these coefficients. Here's my equation, right? And I put it in terms of the expected value of y. So 63 points. So the health-related quality of life is a questionnaire. And I forget what scale, it might be on a scale of 100. So 63.11 is the average for folks who don't exist, but would have 0 age and 0 STAI. So again, not super interpretable. The negative coefficient for age, what does that tell us? As age increases, what happens to the expected value of health-related quality of life? Does it increase or does it decrease?
It would go down.
Right. And so our negative coefficient means as our predictor goes up, our estimated value for the outcome will go down. So this just says, right, that's kind of commensurate. Now, sometimes you might get a small beta, but it's significant because you have a large data set. In this case, the data set's actually pretty large. This value isn't really, I don't think it's really practically significant either, right? So as for every year that you age, your health-related quality of life goes down by 0.047 on that scale, which is a very small amount. Same thing with anxiety, right? It's got a negative relationship, so that makes sense, right? And we saw that in the correlation matrix, right? Negative relationship. As anxiety goes up, health-related quality of life goes down, or as health-related quality of life goes up, anxiety goes down. So we see that here now, right? The difference, remember, between a correlation coefficient and a regression coefficient is a regression coefficient is on the scale of measurement that we're on, right? So we can interpret this as someone goes up 1 unit on the anxiety scale, we'd expect their health-related quality of life to go down by 0.847 units. And so that's got a small p-value, meaning we have, a fair amount of, we can be fairly confident that there is a negative effect there. But we might ask, is that practically significant? Do we care about that? Now, this is adjusted for the presence of age in the model. So if one thing you'll notice, if you start to fit, so Mike, if I decided, yeah, let's just get rid of age, it's not doing anything for me. Let's just do a simple regression with STAI total and health-related quality of life. So I take age out as a predictor. I just have one predictor. This number is going to change slightly. Now with this model, age is not significant. STAI is. Take age out. This number is not going to change too much. It'll remain negative, most likely. Especially knowing, seeing here that the correlation is pretty strongly negative and that age doesn't seem to relate to health-related quality of life or anxiety scores, then, keeping age in, taking it out isn't going to change the estimate too much. But we're going to see a second example in which taking a predictor out or leaving it in makes a big difference substantively on a regression coefficient. So to summarize, when we start to add more variables, we still have that same interpretation of the betas as our predictor changes by 1 unit, up or down, well, really up as it goes up by 1, right? Then our outcome changes. So if we have negative, it means we can expect our outcome to go down by that amount, or if it's positive, go up by that amount. Everything else is just as we used to have it. We have a t-test for each predictor, and we can have a confidence interval. Again, the confidence interval is going to agree with the p-value in terms of if my confidence interval, because remember, what's the null hypothesis here? Null hypothesis is that these betas are 0. And if they're exactly 0, then that just takes the, that's equivalent to fitting a model without that variable. So if I look at my confidence interval, right, I can see here 0 falls right in that interval, which matches up with age not having with age having a high p-value. Whereas here, this interval we'd say is bounded away from 0. Right? The highest, the upper bound for our interval is -661, -0.661. The lower bound is -1.032, right? So 0 is all the way over there. Not a plausible value. That corresponds with my low p-value. And then, so here's, right, let's just to solidify this, because it is important, and Stephanie asked about it last week. STAI is on some, I forget the full range, but let's say it's on a scale of 1 to 10. Let's get the expected value of someone who's 40 years old with a STAI score of 2. So how do we do that? We plug the 40 in here, we multiply it by 0.047. We plug the 2 in here, multiply it by 0.847, and then do the subtraction. Why doesn't everybody try that? Whoops. So I want I don't know how to make that bigger, but I'll figure it out. Again, well, we would get expected value of y when age equals 40 and STAI is 2 by taking our intercept, subtracting 0.047 times the person's age, which is 40 years, minus 0.847 times the score on STAI, which I have said is 2. Right? And then you just do that math out. Let's see what we get. Minus 1.88 and minus 847 times 2 minus 1 minus 6, 9, 4. Let me get, oops, 3.11 minus 1.88 minus 694. So we would expect this person to have, or the model predicts, right? So this would be, this is, right, we always use y hat, right? The y with the little caret on it, right? This is y hat for that person. And then of course the residual for that person is their actual y value minus y hat. And that's, again, how much we're off. And these coefficients, the formulas that lead us to these numbers, are designed to minimize the average of those prediction errors. So we're on the same ground that we've been on since week 6. We're now just adding a little bit of complexity. Okay, so with numeric variables, this part, a lot of it is pretty easy because we're going to have one predictor per variable. Interpreting it is a little bit harder, but it's it's still pretty straightforward. Most people, what they do, right, is they say, okay, so this is the effect of STAI on health-related quality of life. It's negative for folks who are at the average value of everything else. right? So we might think of people of average age. This is the relationship there between STAI and health-related quality of life. Okay, questions on interpretations and stuff before we move forward? All right, good. So the next step is to then include or merge this with what we know about categorical variables, right? So we're going to go back to week 6 now. If you remember in week 6, we weren't live, but you watched a video where I used this example about looking at the relationship between a patient's age and their bone mineral density, which is important in osteoporosis. In that example, the beta coefficient was very slightly positive, which doesn't make a lot of sense because, again, osteoporosis, when you're more at risk for that when you're older, and also when you're female, right? The question is, well, does that make sense, right? From a scientific perspective, since this isn't a randomized control trial and age isn't assigned randomly, we can't say that getting older is causing higher bone mineral density. Even without a small p-value, we're not seeing what we would expect, decreasing bone mineral density with age, right? So this is a common situation, right, where we've got a weird effect. Something's happening in our data that we wouldn't expect. Right? Sort of the process, the physical processes that we're looking at would suggest a negative relationship. We're not seeing that. So maybe there's something going on in our sample. And so what I'm going to clue you into on here is kind of the converse of Mike's question, which is very important in multiple regression, in observational research, is this flip side of our beta coefficients aren't going to be, they're going to be biased, which means they won't be equal to the true value if we don't include all the important predictors that are out there, which of course we can never truly know what all the important ones are. So let's take a look at what happens in this case when we add to our model. So remember, this was the model from week 6 with a slight positive effective age, although not a great model, but still sort of odd. We might think that there's something else going on. So let's add another variable that we might think would be related to bone mineral density, and that's weight. When we add a person's weight to the model, we now get a completely different result. Take a look at what happens to the coefficient for age. Whereas initially it was positive, although small, now it's negative. The p-value also changes, right? So that's a typo from the book. It should say now, right? So instead of the p-value for age being 1.47, p-value is now 0.028. And our R squared goes from 0.05 to 0.465, which is a big change. Let's take a look at a few plots to see if we can understand this, right? So this is the initial plot of the scatter plot of data from week 6. And we see, the trend line is positive, but the relationship looks kind of weak. Okay? Here's a situation in which there is a lurking variable, body weight, that's highly correlated with age. And maybe we should include it in our model. So here's a scatter plot of the relationship between the two predictors. And now they are very correlated, unlike the previous example. Indeed, I can get some better insight if I do, remember back a few weeks, I had you make some scatter plots with different groups, different lines for different groups, right? Or the points were colored. So I don't have a categorical variable here, but let's say that I made body weight categorical. Here's a plot where I make a new dummy variable in my data set. Is the patient over 156.7 pounds, right? So blue is no, green is yes. If I then go ahead and fit the regression line in both groups separately, they're going to be parallel, so they're going to have the same slope, right? Indeed, it's that same negative slope. It becomes negative because now I have some new information. I'm essentially stratifying by weight in my model, right? So I'm first acknowledging the relationship between bone mineral density and weight. And then I'm using the leftover information to look at age and bone mineral density. And when I do that, I see the true situation come out. Right? This is something that is often referred to as Simpson's paradox. And the lesson here is in looking at data in which there's sort of some lurking variables, especially grouping variables. Not including those variables can give you a really skewed look at the picture. And so generally, in multiple regression, we do try to include as many variables as we can to avoid that situation, to make sure we see the effect clearly. So when we plot, so what we're doing in multiple regression is we're essentially saying, right? So in our, actually, let me open up the data set and illustrate to this to you a little bit more, because I think that'll also be helpful. Just give me 1 second. Now, I didn't include this in your materials, but I could upload it if you want to play around with it. Oops.
Just while you're opening that up, why is it intuitive that those lines are parallel?
So it's probably not intuitive. The reason lines are parallel is because we're not fitting what we call an interaction model. So next week, what we'll do is we'll allow for these lines to potentially not be parallel. So that's another assumption of our multiple regression model as it is this week, which is that the effect, in this example, the effect of age is the same in different groups, in different strata of weight, right? Which is the same thing here. The effect of STAI total, even though age is a numeric variable, we would still interpret this as or this model is basically fit, assuming that this effect of anxiety is the same at every different age in our model. So next week we're going to learn, and that's an empirical question, right? Which we often don't know. So actually the fitting multiple regression models, actually finding the true model can sometimes be a really big hassle because we have to worry about these so-called interaction terms. And again, we're going to learn about those next week. One way to know if they exist, so in this data, they don't, right? If the lines weren't parallel, then we would know that. Right? So if you plot your data, and so it won't come out in this data set, we can go ahead and just, I'll come back to that. We have a few more things to talk about here. Let's see if I can capitalize on this now. Where are my data? Here we go. Let's look at the practice data set. We'll see a preview of this next week, but All right, so we're going to look at, just from a graphical perspective, simple scatter, or it's the overlay. Let's see. Image, label cases by oops, that didn't do it. Well, we're not seeing the different cases. Okay. It's a simple scatter. Right, there we go. Wrong variable. There we go. Now we're going to add okay, so they are pretty much all. That's better. No, I want linear. Interesting. So here you can see, now I put these garbage lines on there. Sorry about that. You can see that the equations are slightly different. So the slopes are a little bit different for these different genotype groups. You see that? Slightly different. And there looks to be almost like a fanning effect, right? So in fact, for practice, when we fit our regression model, our results may be a little bit inaccurate because of the potential presence of an interaction. This may not be a huge deal in our model. So one way we could do that is just, kind of fast forward to next week and do what we're going to do next week and see if that sticks to the wall and then interpret. But generally it is a good idea. So this is sort of, we back up a minute. It's this example of Simpson's paradox. Again, it sort of is designed to illustrate, that it's important to include, all the relevant predictors you can, in at least as your first attempt at fitting a regression. And then also, it's probably a good idea to play around with graphics, to try to graph your data. Here, what we're doing is we're attempting to graph it in 3 dimensions, right? So we're basically looking at age, the age BMD relationship for 2 different settings of this weight variable, because it wasn't a grouping variable. If we simply just have a grouping variable, then it's easy. We just separate the cases in groups and see if the regression lines are parallel or not. So we'll talk about that more next week. All right. One other thing I do want to talk about, but I'm not going to waste time in showing you the equations and stuff, is um, technically we call these partial regression coefficients, but usually we just call them regression coefficients or multiple regression coefficients. And so in correlational analysis, the analog is a partial correlation coefficient. And all this is it's more of like an effect size. So the regression coefficients are on our scale of measurement of bone mineral density. Correlation coefficients are on a standardized scale between -1 and +1, right? So, you know, they're not really used that much anymore, but if we wanted to use them, what we're doing is, this is the way you read this is a partial correlation between BMD and age controlling for weight. We're partialing out weight. And it's negative. It's not super strong, but it's negative. So the true, right, and that we see that in the graph, that matches that linear relationship in the graph, right? And then similarly, the relationship between BMD and weight controlling for age is positive, right? So as your weight goes up, your bone mineral density goes up. It makes sense. So you may see these in publications, not a ton. I'll show you how to compute them. Generally, you know, the multiple regression models are more interpretable, but these work better as effect sizes. So right, from there, right now, basically, you know, we're just going to continue to add models or add variables to our model, and get back to Mike's question. Ali and Stephanie, it's really a philosophy of science question. It's what are we trying to do? Are we trying to test a theory, in which case we might use theory or prior results to guide our variable selection? And only, you know, one thing that is common and should be done more is to try to replicate an effect that another author has presented. And so probably the best way to do that would be to collect the same type of data and then, you know, fit the same regression model with the same variables that the previous author used. It may not be the best approach, but that allows you to really get a sense as to whether or not the effect will show up in a different data set. So some people take that approach. Medicine, it's kind of been, health has kind of leaned more towards this. Variance explained in predictive accuracy, and then also just like adjusting for confounders, right? So, you know, adjusting for confounders ends up being like a whole thing in itself. And it's great if you have thousands and thousands of patients in your study. If you've only got like 100 patients, there's an issue as you start, depending upon who you talk to, the ratio of the number of people or data points to predictors, you should have like 10 or so people for every predictor. So if you have 10 predictors in your data set, you're going to want to have at least 100 people total enrolled in your study. And the reason is because, again, in a high dimensional problem, in order for the math to be precise, you've got to have a lot of information. Each variable's got to have a large range, capture, you know, all possible age ranges, weights, bone mineral densities, whatever else. So that can be an issue too. If you have a small data set, sometimes it puts a damper on how many predictors you can have. One thing that is true, and we'll discuss this next week when we talk about how to compare different regression models, is you can never make a regression model worse by adding more predictors. You're not necessarily making it better, but in ordinary regression, we use R squared as our measure of fit. R squared can never go down when you add predictors. It might not go up by very much, in which case the predictor doesn't matter. It can never go down. So it's not a bad idea to add confounders. It's just that we reach a limit of the amount of information that we can wrench from a small data set. The other thing is, from the perspective of science, we've always, in the history of science, chosen, if we have two equally well-fitting models, one that's more complex and one that's a little simpler, we tend to choose the simplest one, right? So that's an issue of parsimony. Mainly because it's a little bit easier to interpret. It's kind of better, sort of, it's Occam's razor. The simplest explanation is kind of always the one to be preferred. Never overcomplicate something that can be simpler, right? But that's a scientific stance. It's not a statistical stance. And you could give a data set to 10 different statisticians and they might come up with 10 different conclusions, 10 different models. So we kind of reach this point of like, it becomes more about science and interpretation than one way to do things. Another view is in the book. We don't talk about causal models much in this course. That's really much more of an an epi thing, but very, very important, especially in health data, if we can't do a randomized control trial, to be able to try to get causal explanations from observational data. Again, we've got to have as many confounders as we can measured. If we have unmeasured confounders, we have to adjust our modeling to get better estimates of the true causal effect. I'll leave this here because again, we're going to do a whole week on this, but now that we've kind of gone through most of regression, I'll emphasize again that everything we've done so far, we assume the observations are independent. So in our data set with bone mineral density or the APOE or for homework, no person is in the data set twice. There's no sort of correlations between different people's values. Very, very important, and one that's kind of an assumption that's sort of almost always violated, is that that the true relationship between predictor and an outcome is linear. It's probably almost always false, but the linear model is just so nice and simple that we continue to use it. The outcome does need to be numeric. It's better if it's approximately normal or continuous. It will still work if it's not, but we'll see some of the later chapters of things that we can do to change that. These two are the ones that we're really going to test a lot, along with the linearity. Homoscedasticity of the residuals, that's a mouthful. I kind of hold my breath every time I say it. What does that mean? We'll look at this in week 12. It basically says that for every value for all of the different people in our data set, that the prediction errors are just as likely to be high or low in the same amount, right? That our residuals are pretty much the same size, no matter who is in our data set. So a lot of what we do in testing regression assumptions is fitting a model, saving the residuals, and then plotting those residuals to sort of diagnose, is there a problem there? Another thing that we like is that the residuals should, on average, be equal to 0. A lot of people believe normally distributed residuals are required in multiple regression. They're not, but sometimes it's helpful to see if the residuals are normally distributed. So we'll be dealing with that, as I said, in week 12. I'm kind of waiting till we're done with both ordinary regression, which will wrap up next week. And then the two examples of what we call the generalized linear model that we'll do in week 10 and week 11. All right. So the rest of what I have here is just about SPSS. So why don't we take our break and then we'll just kind of launch into that and stumble around there for a while until we're good. Yeah. All right. We'll do 10 minutes and then come back. Okay. Go ahead.
On one of the questions, it asked for the t-score, or the descriptive statistic t, and was 1255 based on 1255 as the degrees of freedom, or 599.939.
Oh yeah.
And I selected the 599.939 because of the R squared score being 0.011.
Gotcha.
And so I was curious to know why that was kind of flawed thought.
Yeah, let me see which question you're after here. 12.5. Oh, right. What is the t-statistic? The test statistic for p-value for two sample t-tests for equal variances. Yeah, that's a trick. That's an annoying one because let me see, I have to run it again. I forget if the 599, if that's from the unequal variances procedure. So it should have been, that 1255 should have been in the line, because you're doing t-test, right? So that comes
Right.
from, now it should be the same as in, and actually the general answer that will work better for this week is, because it'll be the same degrees of freedom no matter what. If you're just doing a t-test versus simple regression with a predictor, with a category predictor. In a regression model, the degrees of freedom for the t-test are the degrees of freedom that are listed in the error row of the F table. Yeah. Which, yeah, in this case, yeah, well, what's the issue?
It was an R squared score. The R squared was actually 0.011. And so when I saw that, I went back and reran the t-test.
Gotcha.
And then selected the second row, since the p-value was, I read that wrong.
Oh, right. Yeah. So you wouldn't have had to do that. So, because I even said like assuming equal variances, so you could have just ignored. Yeah, you could have just ignored that row. You probably should have ignored that row, because that is accurate. That t-value would be accurate if you use the unequal variances row, but you didn't need to do. I think you overthought it a little bit.
Okay.
Sorry about that, Mike. Yeah.
No, it's just, it's just learning when not to overthink it.
Yeah. The equal variances t-test issue is important. It's almost always like not super violated. So you can, like, for the most part, you can get away with not even worrying about that equal variances assumption for T. Going forward, last week's homework is really about just sort of showing you like, hey, you can use the t-test procedure or you can use the regression model and you're going to get the same results. So like, that was kind of the point. The rest of it you don't have to worry about it. But point being, like, as you go forward, you can generally assume that if you're using a t-test, you could just use the ordinary t-test. And then, as you're looking at the data, you might make a decision to switch to unequal variances if like one group was like way stretched out, and the other group was really, kind of packed together.
Okay. Yeah, I thought I was being really, slick and going back and.
No, that's good. I'm glad that you did that. I'm sorry. I'll I can kind of credit you for that, so I wouldn't worry too much about it. But
I was just kind of curious to know when to pay attention to the R squared score and when not to.
right.
I guess is the and it was really kind of in your statement, I guess is what I'm getting to, is that you had said equal variance, assuming equal variance. So
Right.
that should have then triggered the
Right.
1255 off the error line. Okay.
Yep.
Now I
Yep.
understand.
That's right. Yeah, because R squared, remember, is just is the fit of the regression model. In this case, it didn't matter. Oh, I'm realizing that question 7, I never filled in the rest of the answers. That's good. That was a free one. But that's a good
Yeah, I got
question.
confused on that one too.
Yeah. Oh my God. That's all right. Other questions though about the homework?
Only one I asked you earlier.
Right. Oh, right. Yes. I forgot to say that. I think, Mike, you and Allie figured it out that in this data set, in the PHMC data set, I always forget to mention that, there is a BMI variable that's numeric, and then there's an obesity variable that's categorical. And last week you should have used the obesity variable, which both of you figured out. I will, before you launch into the homework this week, I will check it and make sure that that's clear this week, because you're likely going to run similar models. I actually think this week BMI is the outcome, in which case you can use numeric, but I'm going to just double check on that. All right. So I put a couple of things in PowerPoint, just to sort of, so they're there, but we're going to run through them, which is, I won't read through this, but this is just so you have it. Next week, we're going to actually look at a different way to do regression, just for the heck of it. We're going to continue to use general linear model univariate. I think it's important to mention that SPSS has another menu that says regression linear, and it does exactly the same thing. The difference and the annoying part about it, because this is actually something we're going to deal with next week, because I'm going to show you a little bit about how SPSS can do model comparison. What's annoying about this menu is that you have to code all your variables manually. So if you have categorical variables, you have to make them into the particular dummy variables that you need, the 0 and 1s. And so the linear regression menu can only handle numeric variables. So you'd have to do all of that yourself. The general linear model does it all for you. Now it has those defaults that are annoying, but it makes it a little bit easier to do. And you get your F tests, which are really nice. And that's why you have to ask for the parameters. In this course, again, we're going to continue to use general linear model. Next week, again, I will show you what happens in regression. If you use the linear regression, there is no rule about reference groups. You actually have to pre-code your data using 0, 1, or whatever else, because it interprets everything as numeric. Whereas in GLM, it's got that reference group as the last category, highest numeric, right? One thing that's nice about this regression output is, again, we're going to talk about how to compare what we call nested models, which is essentially what the F tests that come out of univariate do. I feel like next week's a good place to show you that. It's a beefed up way of comparing models based on their R squared. Important is that going forward with linear regression, there's two ways we can test the null hypothesis, right? The first one is regression parameter itself. The null hypothesis that beta is 0, and we use a t-test for that. And the degrees of freedom for the t-test, it's really n, the total sample size minus the number of predictors. But sometimes that's kind of difficult to keep track of, so you can read it right off of the error line of the ANOVA table, and I'll point that out. You can also do an f-test, which comes out by default, and so what's happening with the f-test is you're comparing different models. These pop out by chance. Sort of generally, if you have a factor or categorical variable, the f-test is a little bit more helpful, unless it's only two categories, then the beta test is easier. Whereas a numeric variable, we usually look at the beta because it's more interpretable. So I'll talk about that when we fit our models. Last thing, and you won't have to do this week. I don't believe you have to do post hoc tests this week, but again, I think I showed you last week. You can get those from anytime you have a categorical variable. There's a post hoc button in the GLM univariate. So if you needed to fit a more advanced model and still wanted to do post hoc tests for your factors, the post hoc tests do adjust for the presence of the other predictors, so they're nice. You can also use different numerical schemes and use the regular regression to test different comparisons if you want to, but we're not going to do any of that. We're going to stay with GLM univariate this week and just build on the last 2 weeks. So, same practice data set as last week, new practice problems. I'll open them here. So we'll just these have the answers too, so you can sort of I'll go through the first one, and then you might look at, well, maybe the second one's a little bit better. Well, we might have time to do both, but anyway, point is we've got it, right? So yeah, let's just go through the first one. We'll do baseline HDL and BMI, and then we're going to add okay, all right. So we'll get some results for BMI and HDL, and then we'll go on to adding the factor. So we'll I'm just going to kind of skip through some of this. We're not going to do the ANOVA and all of that. We're just going to look at the correlations and partial correlation, and then jump to question 2. Let's take a look at our data set. All right. So first things first, let's look at the partial, what do we got? The partial correlation between age and baseline HDL controlling for BMI. Okay, cool. So we've got age, this is baseline HDL, HDL pre, and BMI. So what did I just say? My brain is starting to not work with me. Controlling for BMI, okay. So under analyze correlate, you see that week 6, we did bivariate. So might as well just do that first. So we'll do age, BMI, HDL pre. And we'll see that BMI and age are positively correlated, right? HDL pre and age doesn't look like a strong correlation, but BMI and HDL are also correlated. So we have if we were using age and BMI as predictors, they are correlated. So it might be good to have them in the same model. The zero order correlation suggests that age and HDL pre did not correlate, but HDL pre and BMI correlate. Now let's take a look at what we call the partial correlation. So this is basically a way to preview what would the regression coefficient be for age predicting HDL if we have BMI in the model. So we go down to correlate partial correlation. And the variables box, we put the two variables that we want to look at the correlation between. So we want to look at the correlation between BMI and age. And then in the controlling for box, BMI, HDL pre and age, controlling for BMI. And that's all we need to do. Interestingly, the partial correlation between age and HDL pre with the correlation between BMI and HDL pre removed, right, is actually significant. It's negative. And so here we've got another case of the presence of a confounder is masking a relationship when we look at these raw or what are sometimes called zero order correlations. So this clues us into the fact that, in order to really get a good look at the relationship between age and HDL at baseline, we really should have BMI in our model, and probably vice versa. So now let's fit our multiple regression model just with these two numeric predictors. General linear model, univariate. Our dependent variable is HDL pre. And we've only got numeric variables, so they go, remember, in the covariates box. So BMI and age. If you remember nothing else, we want to click options, parameter estimates, or else we won't get the regression equation. And then it's always nice to have descriptive statistics, although usually that's just of the outcome. Now, one thing that you may want to be able to do for homework in addition is click Save and click on Unstandardized Predicted Values. What this is doing for us is it's filling out the equation that we're going to fit for every value that we have in our data set. So I'll illustrate that. I'll go ahead and save the residuals too. That's how much we're off. So you don't need to do that for homework, but there may be a couple of problems where that would be helpful to know how to do that. So if you want to get the predicted values, what this does is it adds them to our data set. Click Save. But by default, that's not there. Let me reset. And whoops, I don't want syntax. No, thank you. Let's do it all over again. So my dependent, HDL, age and sex are my covariates. Remember covariate because they're numeric. Always options, parameter estimates. You can get this too. And then I'm also going to ask for the predicted values, unstandardized, and the unstandardized residuals. Click OK. So first and foremost, if I was going to report the t-values for the parameter estimates, the degrees of freedom that I use is the one in the error line, degrees of freedom 77. So each of these t-tests has a degrees of freedom of 77. Whereas if I was reporting the f-test, say for BMI, that would be an f, remember f has two separate degrees of freedom values, an f of 1 and 77. So remember, for in our table now, what do we got? The top row is the f-test for the overall model. Does is basically, are the predicted values helpful? And so this corrected model line, that relates to the R-squared value. Generally, if this is significant, we'd say R-squared is significant. But you don't always report that. It's just helpful to kind of look at it. We ignore the intercept line because we're not testing a hypothesis, just the same way we ignore it here. We don't test hypotheses about the intercept. It's pretty much almost always going to be significant because usually you don't have a variable that has a mean of 0. So we skip right down to just our two predictors here, and we see based on our f-tests that they're both have p-values under 0.05. So age has an f of 5.039, p of 0.028. So we'd say, okay, there's evidence of an effective age. Same with BMI, evidence of effective BMI. Now, again, for numeric variables, and indeed for categorical variables, the f-tests don't tell you the direction of the effect, right? So in order to know like what's actually happening, I have to look down at my parameter estimates, right? And I see that the parameter estimate for age is negative, right? So as age goes up, HDL pre tends to go down, which is kind of interesting. But that's controlling for BMI. So that's fixing BMI at some level. As patients' ages increase, their HDL tends to tick down just slightly. Other direction, if I freeze age at the average value, there's a positive relationship between BMI and HDL. Those who have higher BMI tend to have higher HDL pre. And again, we can interpret it in terms of unit change too, right? So as BMI goes up by 1, we would expect HDL pre to go up by 0.5 point as people, so for every year that a person ages in the data set, their baseline HDL goes down by about 0.25. So that makes our estimated regression equation so I'll type it out to HDL pre, and then that vertical line means given the predictors, age, you can separate them by commas, BMI equals 43.27 minus 0.280 times age plus 0.490 times BMI. Okay. So there we got our estimated regression equation. So given, if I take a person at random, or you could fill in your own age and BMI in here and get a predicted value for your HDL baseline if you were in this study. All right. Whoopsie. Oh, screwing everything up here. Zoom is getting mad at me. Hold on one second. I always forget when I have annotate on, I can't do other things. So hold on one second. Okay. Good. So this is the same output as you saw last week. The only difference is now instead of having just dummy variables, we've got 2 different numeric variables, but everything else is interpreted the same. So questions about the output or getting the equation, all that stuff. All right, cool. Let's talk about inserting values in here and how that works, and then how that relates to what I asked for in the output. So if I go back to my data set, I'm going to see two new columns, pre-1, res1, pre for predicted values, R for residual. So let's just talk about what these are for a second. Okay, this is literally the regression equation for this person one. Okay? So all we've done there is, and of course I minimized that. Let me get that back. Okay, so you can see our output. You can see the output again. Yeah, all right, good. Let me retype that equation. There we go. So let's take a look at this person. Right? We know their BMI. We know their age. Here's their observed HDL pre. So their actual value of HDL pre is 41.2. Okay? Let's see where this 43.91 came from. That simply comes from just inserting this person's values. So we've got 43, right? The value of the intercept is the same for everybody. This person's age is 32, so we get 0.280 times 32, plus person's BMI is 18.4825, and we'll take it all the way out so that we don't have rounding error. 490 times 18.8425. So if you do this math out, you should get 43.91 on the dot, or at least rounded there. And you could do that for anybody in the data set. Right? So if you're curious, so rather than picking values at random, like let's say you find somebody who represents, an interesting case, somebody who's 40 but has a BMI that's really high, you don't have to necessarily compute what it would be. You have a column of predicted values there. And then, of course, the residual is just their observed value minus the predicted. So it's always observed minus predicted. So this person has a negative residual because their predicted HDL was larger than what it actually is. Okay? So based on the equation, we overshot for this person. So we have a negative residual. Here's somebody where we have a positive residual, we undershot. So this person, age 38, BMI of 25.73, the equation or the regression model predicted that they should have an HDL of 45.78, when in fact they had one that was higher, 50.6. So we undershot, so we have a positive residual, which is kind of weird, right? But you have to think about it graphically, right? So the regression line represents, or in this case, a plane represents the prediction, right? So, and the residual is the distance, negative or positive, from that line, right? So if the line is at 45, but the person's data point is at 50, then that's a positive residual, right? They're above the line. In this case, the line's at 43, but the person's at 41, right? So the line over predicts they're lower than the line negative residual. Sometimes it's weird to figure that out, right? So this is to say that, if you're ever asked, what's the value of the regression, what's the predicted value for person X who has, BMI of, trying to delete that one. A person who has a BMI of 26.15 and an age of 43, you can crank out the, you can compute it yourself, but so will SPSS. And then it also gives you the residuals. So it's a handy thing to do. And then in week 12, we're actually going to use these values. We're going to graph them. Might as well do that now just to show you kind of a quick and dirty thing you can do, which is to just kind of look at their behavior relative to the outcome. So our outcome is HDL, and we're going to do a scatter plot where HDL pre is on the x-axis and the residuals are on the y. Well, this is definitely not what we want to see. We would not want to see that. What we would like to see is for all the values of the outcome that the residuals are sort of uniformly distributed. So what we want to see is like a noise. We see a trend like this, then something's wrong with our model. So we'll leave that for week 12. Okay. So now let's talk about adding factors to the model. It doesn't change too much what we do, but it does make it a little bit more complicated. So going back to our, kind of slow down a little bit and walk through this. Okay. So we say, as a last look at the underlying physiology, we wish to look at the relationship between APO genotype and baseline HDL. Right? Given what was seen previously, we'd also like to control for subject BMI. First question, what is the name of the kind of model we use to answer this question? Now, we didn't discuss this, and it doesn't really matter, but when you mix, or when you have a central question about a categorical predictor, and you want to include one or more numeric predictors to kind of control for, we call that, in the olden times, we call that analysis of covariance. Analysis of covariance, or ANCOVA. Really, it's just still multiple regression. But in sort of before it was seen that it really didn't matter what you called it, it's still regression, people used to refer to that as analysis of covariance. Let's first look at the average level of HDL for each genotype, ignoring BMI. Then what we're going to do is we're going to fit a regression model, including BMI, and seeing if that kind of differs a little bit. Let's go back to our data set. And we'll just get, we'll use explore, HDL, and our APO genotype. So we find that E2, those folks have a mean 46.66-ish. E3, those folks have a mean that's slightly lower. And these folks, E4, not a huge difference between 3 and 4, but they both seem to be a little bit lower than E2. And of course, we looked at that last week for practice, right? The question is, should we be, this is without regard to BMI. Now we know that BMI and HDL are correlated. When we fit the regression model, we saw that. So the question is, if we adjust for, or we control for BMI, will the model give us slightly different estimates than these differences between the sample mean? Here's a nice look at the box plots. So before we jump into that, let's remember, and here's where it's going to be important to first write out the regression equation before we get the results, right? So we're gonna use multiple regression to predict baseline HDL using the genotype and BMI as predictors. Let's work first just with this model. In fact, if you're following along, oops, the document on Canvas, you can peek at the result. You can peek at the answers, but let's sort of entertain this for a minute. So, write out the multiple regression equation. The implicit in that is writing it out the way that that SPSS is going to fit it, right? So, if you remember, SPSS makes the reference category the alphabetically last or numerically last category. So with this variable, it's kind of tough because it's got an E and then a number. So you use the number. So it's going to be, the reference category group is going to be E4, right? So just like homework or just like practice last week, we're going to have a dummy variable for E2, dummy variable for E3. So that's important. So, when I ask you this for homework, write out the equation for the prediction. This means before we get the numbers, basically I'm asking you to make sure you know what the dummy variables are. Okay. So in this case, we'll have expected value HDL. I'll just give an X and just shorthand it. We're going to have the intercept, so beta, we'll just say beta 0 plus beta 1 times a variable called E2, an indicator for the E2 group, plus beta 2 times an indicator for the E3 group. Remember, E4 is the reference group. And then beta 3 times BMI. The next question says, what are the equations for the expected values of the 3 APOE genotypes? Right, so this is a little bit more involved, right? We're going to keep BMI in the model. We're just going to set each of these equal to 0, okay? So for the E2 group, we set E3 equal to 0. So it's the expected value of HDL given BMI and E2. The mean HDL for group E2 is simply beta 1 times E2 plus beta 3 times BMI, right? So the important thing here is now if we want a mean for each group, it's going to be relative to BMI. We need to use BMI. It's going to have a BMI value in there. Similarly, if we want the expected value for E3, we set beta 1 equal to 0, and now we have beta 2 for E3, but we still leave BMI in the model. For group E4, remember we set both of these equal to 0. Their mean is just the intercept, And then if we want their HDL, we do have to incorporate their BMI. Right? So the idea here in analysis of covariance, or when we have categorical variables in our model, is their betas are going to represent, as they did before, differences between reference and indicator group, but now controlling for the presence of BMI, or adjust the equations and continue to include BMI in them. So you're going to adjust that expected value based on the person's BMI.
We're not able to see what you've typed for some reason.
Oh, that's weird. That's annoying. I wonder why not. Why not?
Now we can.
Is it not till I stop typing it? Oh, that's so stupid. Sorry about
I think
that.
so.
Oh, that's so dumb. So what I was typing is, right, this is our full equation here, the top one. And then to get the equations for each group, for E2, we set E3 equal to 0. That beta goes out of the model. And so the expected value for HDL for E2 is going to be beta 0 plus beta 1. Really, it's just plus beta 1. We don't even need the E2 in there. Oops. Annotate. Annotate is failing me tonight.
Why would we not need the E2?
Because it's already set to 1. Let me explain that. That was the point of me doing this. So remember, in this equation, when you have categorical variables, you're turning them into 0, 1 indicator variables, right? So if a person's in group E2, they're going to have a 1 on the E2 variable. They're going to have a 0 on this one. So if you want the mean for the E2 group, in the equation, you insert a 1 here, a 0 here, and you don't know their BMI, so you leave it there. And so the equation becomes beta 0 plus beta 1 plus beta 3 times BMI. Or you would combine these two and you'd have a number plus beta 3 times BMI. Similarly, for group E3, those are the folks that have a 0 on this variable, but a 1 on this variable. So you insert those values, and now we get beta 0 plus beta 2 plus the BMI 1. And then, of course, group E4, the reference group, is indicated by zeros on both. So they both leave the equation. We're left just with the intercept and beta 3 BMI. So let's actually fit the regression, and we'll compute these things. So I'm going to move them somewhere inconspicuous. But we'll save this. Actually, you know what? Sometimes it's easier to just do it in Word rather than annotate. So that's what we're going to do. Oops. Wait, I want to clear everything. Hold on. There we go. Okay. I'm just going to share my whole screen. It might get a little small, but that way you can see everything. All right. So let's go ahead and get these betas and make this make sense. So get rid of age. We're not going to use this in the model. APOE is a fixed factor, right? It's a categorical variable, so we put it there. And we're not going to worry about the residuals. We'll just get rid of that step. Just make sure we're getting the parameter estimates. And click OK. Here's our means, as we said before. Now, because APOE is a factor, it's represented in our F table with just one line, but with 2 degrees of freedom because we've got 2 dummy variables there, 2 equalities, whereas BMI shows up in our table with 1 degree of freedom. Notice the error degree of freedom has changed because we've got basically a different number of predictors. We've got 3 predictors instead of 2 before. And so here's our new equation. Let's transfer that over here. So our actual equation is $36.766. Now, of course, the betas are in, anyway, beta 3 is now beta 1, unfortunately. So let's rewrite this because SPSS is being stupid. Apparently, it likes to put the numeric variables first. Good to know. Always find new things out of SPSS as I continue to use them. So this would be beta 2, beta 1 times BMI. There we go. Okay. So our beta 1 is 0.350. It's not significant, or it is significant. The other ones aren't. So of course we'll leave in the model. The coefficient for E2 is positive, 0.957, but the coefficient for E3 is negative. Remember, these are comparisons between each of those groups and E4 only. We got negative 0.221. Okay. So now let's do what we did before. Right? In the model, even though the data set is coded in the way it is, what we've done here is we've said, no, our model is going to have a dummy variable for E2 and a dummy variable for E3. So E2 equals 1, E3 equals 0, just to make this more explicit. This is what we're doing when we want the expected value, the mean, this is basically what we call a marginal mean or an adjusted mean for group 2 or group 1, excuse me, E2, right? Because we just now insert our estimate. So we get 36 there. I'll make this explicit too, times 1, beta 2, which is the coefficient for E2, times the value of E2, which in the background is 1. And then E3, these folks have E3 equal to 0, so beta 3 doesn't make it. Actually, just remove the 1. And then we insert our slope for BMI. 0. So in practice, then you would add these two together, right? So because we're left only with numbers there, we can combine them. So basically what this does is it changes the intercept, and then we're left over with the BMI effect. Right? So the expected value for folks in this group, we'll do 36.766 plus 0.957 equals 37.723, right? But then, because there's a positive association between BMI and HDL, we leave that in there and say, well, we could expect that people in group E2 sort of have a baseline or whatever. Their HDL is a function of the overall average for the group plus some effective BMI. We then do the same thing for group 3 by or E3 by just using that coefficient. So now the intercept comes down. Beta 3 comes down, but that's negative. Negative 0.221. And then again, we always have at the end is 0.350. Now we're subtracting from the intercept 36.776 minus 0.221. Oops. 36.5. And the final one is just the intercept itself. 36.766. So what we've actually done here is we've actually produced the equations for the 3 lines that would be on the plot. Notice they're all going to be parallel because they all have identical slopes. What differs is just their intercept. So when you have a categorical variable in a model with a single numeric variable, what you're essentially doing is getting separate equations for each of those models. And the test is really a test of whether the intercepts for those equations differ, right? i.e., are they spread apart or not? Now, remember, when we graphed this, we found that they weren't. So we'll go ahead and graph it again. Really wasn't a big difference. So we're gonna reset this. BMI DLP. Again, if we add our lines for the different groups. Oh, they do. Actually, that's interesting. They shouldn't cross like that because that wasn't in the model, but they must do this a slightly different way. All right, so now they should be parallel, but we're going to see next week that that our model is incomplete. Interesting. I wouldn't have expected that. So this comes from our data. If we were to plot our model, those lines would be parallel. So sorry, I don't mean to be confusing, but yeah. So this,
I guess I am kind of confused in terms of why they're doing that, since the slope is the same for each line.
right. So I wonder if I can.
The equations that are written there are different, though. One's 0.34x and 0.54x.
So again, we find out more things about SPSS. So what SPSS seems to be doing is instead of using the model to produce the lines, it does regressions, 3 separate regressions on subsets of the data, which is somewhat annoying. I guess it's helpful to empirically see that on the different subsets, the lines are not parallel, but then that's confusing when you try to graph it for exposition. So this is actually a good teaching moment, right? Back to our model. Our model is fit with the assumption that the lines are parallel, right? So the regression model that we fit this week has an assumption that these lines are parallel, that there's no interaction between the different variables, right? That the effect of BMI doesn't depend on what genotype you have. If we were to use a graphical program that put these equations on a graph, these equations, we would have 3 parallel lines. SPSS instead, what it does is it takes the scatter plot, it knows which data points come from which groups, and it fits, as you can see, 3 different R-square values, which are different from here. Right? This is the main model with both, with all the data has an R-squared of 0.121. These are 3 different models. The first model, and I can't really tell which color is which, I think it's this line here, is using only the data from E2 and regressing BMI on HDL-pre. Then here we're using only the data from E3, which is this darker line here. And that line's actually pretty flat. And then E4 is back there. So this is an empirical look at our data in which within each group, the lines are not parallel. This is our model-based, this is our model assuming the lines are parallel. So our model is bad. So next week, we're going to explicitly test what happens to our model when we include this interaction term, right? Where we allow the lines to not be parallel. What will our model look like? So sorry to confuse you there. I was hoping to see the 3 parallel lines. It dawned on me as we were doing this part that that's what we're writing out. So if you graphed this with pen and paper, you would have to make the lines parallel because the slopes are the same. Whereas if you go ahead and subset your data and ignore the rest of the groups and just fit the data within each group, you get these non-parallel lines, which we'll deal with next week. So things to do this week are the normal F-tests, parameter estimates, but then working with the equations this way and getting expected values, or, you know, I might go one more and say, well, what's the expected HDL for someone in group 3 with a BMI of 23? Okay. So to compute that, I would just insert 23 here and then continue the multiplication and I have a number. And that's it. You're not going to have to plot the data or do any of this fun stuff. It's just a preview of next week. Okay. But I do want to reinforce this part, you know, to be comfortable with the equations and this dummy coding, which can be confusing, right? It's like, well, where do we get these 1s and 0s from? Or just remember last week. And remember, you know, what's annoying, I think, about, or what can be difficult about regression with categorical variables is remembering that your data are coded one way. So here we have a data set in which we have the letter E, the number 2, that's one group. The letter E, the number 3, that's another group. To fit the regression model, we have to make a choice. What numerical coding is going to represent this grouping? So we choose this dummy procedure where in the model and in our equation, we're no longer using E2 and E3 as values, it's 0s and 1s. And to make sure you keep track of, like, okay, when I want the mean for group E2, okay, or I'm filling in, you know, somebody who's in E2, that means this whole coding scheme that goes into effect. I have to insert a 1 in my equation for E2, a 0 for E3, and remember that E4 is represented by the intercept. So hopefully those, you know, when you run up on those questions this week, homework, just shoot me an email if you run into trouble. I'm happy to hop on a Zoom to chat about those. Other questions? Okey doke.